Okay, so we're going to start off with letter A. To measure the change in enthalpy for lithium chloride, the student adds 100 grams of water, initially at 15 degrees Celsius, to a calorimeter and adds 10 grams of lithium chloride, stirring to dissolve. After the lithium chloride dissolves completely, the maximum temperature reached by the solution is 35.6 degrees Celsius. Now in part 1, it says to calculate the magnitude of the heat absorbed by the solution during the dissolution process. Assuming that the specific heat capacity of the solution is 4.18 joules per grams degree Celsius, and it also wants you to include units with your answer. Now, when it asks me to calculate the magnitude of the heat absorbed by the solution, I instantly think of Q equals MCAT, which is MC, change in temperature. And then I go back and look at the problem and I see, yes, I have mass, which is the 100 grams of water and the 10 grams of lithium chloride. Yes, I have temperature also, which is, well, the change in temperature. So the initial temperature is 15 degrees Celsius and the final temperature is 35.6 degrees Celsius. And of course, we have the specific heat capacity. And all of this allows me to use that equation. So I'm going to write the equation down first and then find the numbers to substitute in. So I write down that there's 100 grams of H2O and 10 grams of lithium chloride. And what I'm going to do is add them together to get 110 grams. And that will be the M. So next, I'm going to find the change in temperature by looking at the final temperature, which is 35.6 degrees Celsius, and the initial temperature, which is 15 degrees Celsius, and I'm going to subtract them, getting 20.6 degrees Celsius. So since I have all the values now, I just plug everything in, and in the end, all the units cancel out, and I get joules left, so it's 9,470 joules, and that is my answer. Now moving on to part 2 of letter A, it wants me to determine the value of the change in enthalpy for lithium chloride in kilojoules per mole. I'm going to begin by writing down how much lithium chloride I have, which is 10 grams, and then converting that to moles. I'll convert that to moles by dividing the 10 grams by the molar mass of lithium chloride, which is 42.39, and I get that from the periodic table by adding the molar mass of lithium and the molar mass of chlorine. And in the end, by doing that, I get 0.236 mole. Since I know that the change in enthalpy is in kilojoules per mole, I know I'm going to have to look back to part 1, which has the heat. But since it's in joules, I'm going to have to convert that to kilojoules by dividing 9,470 by 1,000. And so I get 9.47 kilojoules. And then I also see that the temperature is increasing from 15 degrees Celsius to 35.6 degrees Celsius, which means that heat is released. And so the change in enthalpy is negative because it is an exothermic reaction, which means that the Q is negative 9.47 kilojoules, not just positive 9.47 kilojoules. And so I divide negative 9.47 kilojoules by 0.236 moles, and I get the answer, which is negative 40.1 kilojoules per mole reaction. So next, for part B, it asks me to write the complete electron configuration for the Na plus ion in the ground state. So I write down Na plus and I instantly circle the plus sign, which means that there is one less electron. There's an electron removed basically, which is why it's Na plus instead of just Na. So this basically means that we're writing the electron configuration of neon. The first row of the periodic table, which has no neon, so that means I will write down 1s2. And then I look at the second row, and neon is at the end, so I write down 2s2 and 2p6. So the full electron configuration of Na plus is 1s2, 2s2, 2p6. Now on to part C. It says, using principles of atomic structure, explain why the Na plus ion is larger than the Li plus ion. So now I'm going to write down Li plus, and as you can see, it's also positive, which means that we're basically writing the electron configuration of helium. So the electron configuration of helium is 1s2. And then we're basically going to compare the electron configurations of Na plus and Li plus. So for Na plus, there's a full second energy level because of the 2s2 and 2p6. Meanwhile, the Li plus only has one energy level, which is 1s2. So the energy level of Na plus is higher than Li plus. And thus the explanation is that the valence electrons in Na plus have a higher principal energy level than Li plus. And since the electrons in higher levels are further away from the nucleus, this means that the atomic radius of Na plus is larger or greater than Li plus. Next, for part B, it asks which salt, lithium chloride or sodium chloride, has the greater lattice enthalpy, and it wants you to justify your answer. First, I'm going to write down the two molecules, lithium chloride and sodium chloride. And I see that the only difference is one has Li and the other one has Na. So I'm going to compare those two ions. And so I see that the Li plus ion is smaller than the Na plus ion. So this means that the Li plus and Cl minus ion are closer together than the Na plus and Cl minus ion. This means that there are stronger attractions between the Li plus and Cl minus ions, so it takes more energy to separate them. So the full explanation is that lithium chloride has greater lattice enthalpy because the radius of the Li plus ion is smaller than Na plus, which means that the Li plus and Cl minus ions are closer together than the Na plus and Cl minus ions. The stronger Coulombic attractions in lithium chloride take more energy to separate Li plus and Cl minus than the sodium chloride. Now, letter E is easier. It says, below is a representation of a portion of a crystal of lithium chloride. Identify the ions in the representation by writing the appropriate formulas, Li plus or Cl minus, in the boxes below. So you just check the periodic table, and the molar mass of chlorine is greater than the molar mass of lithium, which means that the smaller molecules will be Li plus and the larger molecules will be Cl minus. Pretty straightforward. Now the last letter is letter F, and it states the lattice enthalpy of lithium chloride is positive, indicating that it takes energy to break the ions apart in lithium chloride. However, the dissolution of lithium chloride in water is an exothermic process. Identify all particle-particle interactions that contribute significantly to the dissolution process being exothermic. For each interaction, include the particles that interact and the specific type of intermolecular force between those particles. So the problem gives us that the lattice enthalpy is endothermic and the dissolution is exothermic. So this is basically two steps, the first being endothermic because the Li plus ion and Cl minus ion break the electrostatic attractions between them, and this absorbs heat, so it's endothermic. And then the second step is exothermic, because both the Li plus ions and Cl minus ions display ion dipole interactions with the H2O. So the negative dipole of H2O, oxygen, interacts with the Li plus ion, and the positive dipole of H2O, hydrogen, interacts with the Cl minus ion. And so this ion dipole interaction is highly exothermic. So this releases more energy than what was absorbed in the first endothermic step. So this is why it makes the whole dissolution process exothermic. And so basically the main point is to include that the electrostatic attractions are broken and that there are ion dipole interactions between the ions and the H2O.